Hello everyone and welcome to a new problem of this chapter. This one is called meeting rooms and it's actually pretty similar to one that we have just solved earlier. You're gonna figure out which one I'm talking about. It's pretty easy, but in fact it has a different solution. So this is why this problem is beautiful. Let's read the statement. So, given an array consisting of meeting time intervals which are represented by start and end times, S0, E0, S1, E1, determine the minimum number of meeting rooms needed in order to be able to accommodate all meetings at every moment of time. So, one thing that I should make clear first is that those time intervals could be a little bit tricky because here, actually, we could have written something like exclusively, but it's not actually exclusively because let's take the example, right? So, for example, the first meeting starts at 1 and ends at 5. As you can see, starts at 1, meeting number 0, and ends at 5. It's the pink one, right? It ends at 5, but we won't take into account the moment time as that room being occupied anymore. So we can suppose that at moment 5 everybody left and the room is empty and could be used again, right? For example, if we had only these two meetings, meeting number 0, 1, 5, and meeting number 3, 5, 8, the answer is 1, right? Because we are using one room from 1 to 5, and at 5, when the other meeting starts, that room is supposed to be empty, and it is, and that's why we can do it with only one room. And as for this example, I've drawn here how the time intervals look. And by the way, a pro tip, always when you have problems with time intervals or any type of intervals, it's better to visualize them instead of just working with the numbers, right? So always feel free to draw an OX or a time axis in our case and draw the intervals and see how it looks like, right? So here, as you can see, 1, 5 is this one, the pink one. 2, 7 is which one? This one, the purple one, right? 0, 9 is the blue one. I marked here the indices. And as for this example, let's explain why the answer is 3. And I'm going to do that very naturally and like I am in the real life, right? So if I was in the real life, let's say I was the building owner and I have these rooms, I would have looked at it this way. At moment 0, I see that the first meeting should start. So definitely I'm gonna need a room for that, right? So for now the answer is 1. At moment 1, I see that, oh, another meeting has to start. And I already have this room occupied. So I'm gonna need a second room. I see that 1 minute or 1 time unit later, another one starts. So definitely I'm gonna need one more room as the other two are still occupied, right? Then moment 3, nothing happens. Moment 4, nothing happens. Moment 5, it's interesting because I have two events here. The first event, which is gonna happen before the second one, the blue one, is that one room gets occupied. So at this moment, 3 rooms are occupied, 3 rooms are occupied. Here, now only 2 rooms are occupied, which is great because when the other event comes, I see that, I'm gonna need one room. Well, I booked already. I've, let's say, reserved 3 rooms. So if this were the rooms, right, what do I have? I have the first one still occupied. The second one now is clear. And the third one is still occupied. So what can I do is look at the second room and, all right, I have a room. So no worries, get that room. It's no problem if I use a room that is empty, right? Because let's think about it. Why would I create or make available another room when I don't need to? I'm gonna do that eventually in the future if I need to, but right now, if I don't, that's cool. So 2 rooms were occupied. Now this group comes and of course they will also occupy this room. So let's mark the second room again as occupied. And again, I'm gonna have 3 rooms occupied. Then still 3 rooms occupied. Then at moment 7, the first event is that the purple group will leave the room. So the third room gets occupied, which is awesome. So instead of 3, I have 2 rooms occupied now. And then 1 more group comes in. And what's gonna happen? Of course, I'm gonna give them the room that just became 3. So again, it was 2 for a split millisecond. Now it's again 3 rooms, all of them occupied. I move to moment of time 8 and I see that, awesome, they left. So I think it was the second room I gave to them. It doesn't matter. This became 3. And now the number of occupied rooms is 2. Another group left at moment number 9. The number of occupied rooms is 1, which is awesome, right? Because I have 2 free rooms and it doesn't really matter because anyways, this group will finish here. So this gets also freed, right? So the thing is that I have simulated what happens during the time. And the conclusion that I came to is that anyways, no matter what I do, I'm gonna need 3 rooms in total, right? And why is that? Because at the moments of time 2, 3, 4, at the start, at moment 5, moment 6, on moment 7, I need anyways 3 rooms, right? So the approach, you can see it as a greedy one, right? You can say that you are a greedy business owner and you're like, I'm not gonna give a resource if it's not really needed. So you can start off like I did with 0 rooms initially available, right, for anyone. And when the meeting should start, I'm like, all right, do I need another room? Or do I have 1 free room that I already made available so I can't undo that, right? If I do have a free room, I use that room. If I don't have any free rooms, I'm gonna make 1 extra available and increase the answer, right? So this is one way at looking about this. But yeah, obviously these are just words. We have to put them into code. And we have actually 3 possible solutions for this problem. And I'm gonna start with the most simple one, which uses 1 data structure that we've just learned in this chapter. And that one is actually the frequency array. And why is that? The reason is simple. You see these numbers, 1, 2, 3, 3, 2, 3, and so on and so forth. Those numbers actually represent the number of occupied rooms at each moment of time, as we've said. It's pretty simple to get these numbers. I mean, I don't necessarily have to apply my strategy of going through each moment of time and seeing what happens. I can do something else. I can take each time interval and just update the frequency array. Let me show you how it's done. As you can see, I have drawn an array which has length, the maximum moment of time, which is 11 plus 1. Why is that? Because of course we don't need to know what happens on the moment 12, 13, because I mean, we already know what happens. No event is going to be taken place, right, at that moment. So the thing is, as you've seen in the previous drawing, the green numbers meant how many events are taking place simultaneously at that moment of time. If let's say we have the moment of time 3 and we know 3 meetings are taking place at that moment of time, of course we are going to need at least 3 different rooms in total to be available for that to be possible, right? So what I'm gonna do is I'm gonna take each time interval and update for each moment of time that meeting takes place, I'm gonna increase the value 1, which is gonna tell me that, all right, we've got one more event which is taking place at those moments of time, right? So 1, 5 means that for every moment of time from 1 to 4, right? Don't take 5 into account because theoretically at moment 5 the meeting ends, right? This became 1 now. Perfect, and that's true. I know for sure that one meeting is taking place at this moment of time. Then I take the second interval, 2, 7, and I see, okay, so for each moment of time from 2 to 6, one other meeting is taking place. So as you can see, these ones will become 2. And this is exactly what's supposed to be, because now we know that at least 2 meetings are taking place at those moments of time. So here's what I'm going to do. I'm going to make this ones to be equal to 2, each of them, and the other moments of time 5 and 6 will become 1. Let's take the third one, 0, 9. What's going to happen here? Probably guessed, all the time moments from 0 to 8 have another different meeting going on at that moment of time. So of course, increasing them by 1, right? So here's what I'm going to do. This is 1. This is now 2. All of these are now 3. All of these 2 actually are now 2. And of course, the other moments of time, 7 and 8, they become 1, right? Awesome. As you can see, we already know that at moments time 2, 3, and 4, we have 3 meetings, all the 3 that we've just seen yet. And this is very true. Now, I'm going to take the 4th time interval from 5 to 7, increase them by 1. So it's going to be 3, 3, and 2, 3, 3, and 2. And then I'm going to take 7, 11, and from 7 to 10, increase them by 1. So it's going to be 3, 2 here, 3, 2, and these 2 become 1. Perfect. And our algorithm ends. Now let's take a look at the array. Is it correct? I think it is. At the moment of time 0, only 1 meeting is taking place. At the moment of time 1, 2 meetings are taking place, right? These 2. Moment 2, 3 meetings are taking place. Moment 3, moment 4, the same. Moment 5, the same. Moment 6, moment 7, also 3 because 1 ended, 1 started. Moment 8, 2 of them because 1 ended, 1 of them, and then 0. Perfect. Now, by doing this, having an array which is initially filled with zeros, and then for each time interval, making these updates on these subarrays, we are going to end up with the array which will contain our answer. And my question to you is, what do you think is the answer? Is it going to be the sum? Is it going to be the minimum? No. Of course, it's going to be the maximum, right? Because the number of rooms needed is actually equal to the maximum number of meetings that take place at some moment of time. So the answer is 3, like in our example. So this is the first approach, right? It has a lot of disadvantages in terms of time complexity and also in terms of memory complexity, and won't work for every type of inputs, only for a specific type of inputs. And think about what are those inputs. And yeah, let's then write the code together. All right, everyone, here is the algorithm. So first thing we do is compute the maximum moment of time at which something happens, right? So it's basically the maximum from S0, E0, S1, E1, Sn minus 1, En minus 1, all the 2 crossed n integers from the input. Then we are going to create our frequency array, and that was the data structure that I was talking about that we are going to use. This is basically a frequency array, not in its like classic definition, because we don't count any values or stuff like that, but we also can say that count like I don't know, the number of meetings that are taking place, right? So in a way, it's a frequency array. And it's going to be, of course, initially filled with zeros, exactly max time plus 1, right? And then for each time interval in the input, so for each pair start end from our list of pairs or vector array of pairs, doesn't matter, we are going to go through each moment of time in that interval. So start, end, and of course, here I've made a mistake. I hope you actually have seen it, is start and end exclusively, right? Great. Now for each moment of time, we are going to increase the number of meetings taking place at that time by 1. And then, of course, return the maximum from this array. Now, obviously, I didn't write the maximum function. Maybe in your language, you'll have a function like that, maybe in Python or JavaScript. Or, of course, you can do a for loop. It doesn't matter. Now, let's analyze a little bit the time and memory complexity of this algorithm and see why it has so many flaws. First thing we do is take the maximum from the input. There are 2 crossed n integers, doesn't matter. This is linear time. No problem. Now, also, returning the maximum, of course, you can get the maximum from an array just using a for loop or a built-in function. Both of them go through every element in the array and are linear time. Now, about the actual algorithm, also, let's start with this. Now, we are basically creating an array of max time plus 1 zeros. In terms of time complexity, this is, of course, big O of max time. So, I know max time is not in the input, but we kind of need to define it in order to express this time complexity because it's super important. I mean, maybe you have at most 100,000 intervals, but the maximum time is something like, I don't know, 1 billion. Could be. So we can't just express the time complexity depending on n when we have such a big factor here, right? Or maybe it is something very small, like 100, then that would be the dream case scenario and this solution is actually very good. But let's continue. So we are going through each time interval and inside we have another for loop which goes through each time moment from start to n-1. So here, no matter what, how many operations do we do? Of course, it's gonna be end minus start, right? So the first thing to notice here is that for each time interval in the input, we are making its length number of operations. That's not so good. So if I was to express the total number of operations our algorithm does, it would be a sum of each end point minus the start point for each interval, right? So with I ranging from 0 all the way to n-1. Now, this is the number of operations here. Then we have also n operations here, n operations here. So I'll just write n only once. We ignore the constant 2. And then we also have this max time, right? This is the exact number of operations our algorithm does. But if we want to express this in terms of time complexity, we still have to make an adjustment. And that adjustment, as you know, is taking the worst case scenario into account. And the worst case scenario, if we defined, right, we made a rule that we will have this max time into our time complexity because it's an important thing. We need to express the time complexity in terms of n, the number of intervals, and the max time, right? And yeah, in the worst case scenario, each and every one of these differences is actually max time. Yeah, it's max time, right? So let's say each interval, you are given n intervals and each of them are 0 and max time. Then each difference is equal to max time, right? So we have a total of n differences, n numbers in this sum, which are equal to max time, plus 1 more n, plus 1 more max time. This is a total time complexity of big O of n crossed max time, right? So yeah, between n crossed max time and another max time, obviously this n is not important, is way smaller than the first one, right? So sorry, let's make this a capital T because it's a constant. And this is the time complexity. Now, speaking of memory complexity, we have to take a look and see what are we using besides the input, right? And of course, we are using this big array num of meetings, which has a size of max time plus 1. So the memory complexity is also big O of max time. So big O of max time. Now, you are probably guessing why this algorithm is bad. And of course, it's because of this guy, max time, right? So if the interviewer would give you a problem in which he would say that, you know what, all the time moments, all the integers in the input, the start points and the end points are at most 100, let's say, then that would be awesome because max time, he basically gave you the constraint that max time is in the worst case scenario 100. The time complexity is still big O of n crossed max time, as 100 is a constant, but it's not that small that we can forget about it and say that it's big O of n, right? Let's say if you make an algorithm, I don't know, who makes n crossed 100 steps, I think that's a pretty big difference between that and an algorithm who makes like 2 crossed n steps, right? So the time complexity is still this one, but at least we have solved the memory complexity. And even more than that, we have an algorithm which can be implemented. We have a server, we have enough resources to hold an array or a list of 101 zeros. But if the interviewer told you that, you know what, the values are huge, the end and start points could be something like 10 to the power 9, then not only that, of course, imagine that the algorithm would take like an infinite number of years to run on a normal computer. And there is one more problem. You won't have enough resources to even store into memory this array, right? So the problem here with this type of constraint is that not only you will give a slow solution, you also give one that it's not good at all, unfortunately. It is correct, but it couldn't be implemented on a normal computer, right? So this approach only is feasible for problems like this, where you have, let's say, this kind of ranges and you have to update them, add something to them, I don't know, decrease something to them, change something of them, right? But these numbers have to be so small that they can actually fit into an array of frequencies. This is like the, as we know, the worst part about frequency arrays, because it only works with problems where the maximum value of the thing that we want to store the information for is small. So we are going to come up with an approach that doesn't need this constraint and that has a time and memory complexity that do not depend on max time. Let's see how it goes.